Introduction to integration. So allow me to give you a brief introduction to the concept of integration. Integration can be perceived as the direct opposite of differentiation. So if you recall, differentiation is basically for division. So for integration is actually for multiplication. So let's see. For differentiation, we have a function y. We differentiate it with respect to x. It allows us to calculate the gradient of a graph in the context of a graph. So similarly for integration in the context of a graph, if we use a function like y times delta x in a graph, we are actually looking for the area under the curve or the line, the y function. So I have with me a graph of y equals to kx. So if I want to calculate the area, let's just say I want to calculate the area under this graph from x equals to 1 to x equals to 2. Now this area, if I may zoom in, so it is likened to the value of the area is likened to the value of y. This height is essentially y multiplied by a value of x. So the area is actually approximately y times x. Now this has an issue because this formula is for a rectangle, but this obviously is not a rectangle. So if we may proceed with this idea that it's a rectangle, what we have to do is to shrink this value of x, the width of the rectangle, to a very, very small value. So as we shrink, the area gets more and more like a rectangle. So if I may draw this is likened to a rectangle. So if I shrink more and more, it becomes more and more like a rectangle. So using this concept, I can find the area under the graph between x1 and x2 if I may sum up all the values of y multiplied by its respective narrow delta x width. Okay, so integration would then be used as a summation symbol. This curvy line is likened to a summation symbol where you sum up all the values of the area for y multiplied by a very small width delta x. And this is generally a indefinite integral, where it's a general form. It provides a general equation or function for the area under a curve. Now if I want specifically to be between x1 and x2, I will have to use a definite integral. So the area that I have, this is area indefinite, this area definite, I have to insert the limits. The upper limit x2 is placed at the top of this integral sign, and the lower limit x1 is at the bottom. So based on that, let's look at one example. Here we have two functions, y equals to fx and y equals to gx. So if I want to calculate the area A1, A1 can be calculated by finding first the area y equals to gx between x1 and x2. So this area I calculated would give me, say, x1. And then I calculate the second area with the same limits of x1 and x2, the area under the function y equals to fx, and I call this area x2. So area A1 is actually x1 subtract x2. So how do I put it down? I'm actually able to write it this way. The first function, integral of gx with respect to x over the limit x1 to x2, will give me the area of x1. Subtract over the same limit but integrating for fx. And I can write this in a single integral. Okay. Now what if I want to calculate the area A2? A2, you notice that the area again can be calculated by calculating two areas. The first area is this area. This is x1, this is 0. This is y equals to fx. And the second area is this area. This is y equals to gx. So if I call this area P1, this area P2, the area A2 is calculated by taking P1 minus P2. So over here, we can insert the integral, and notice that the range is different right now. It is no longer x1 to x2 as per the previous area, but it's actually from 0 to x1. Now x1 becomes the upper limit, so it's written at the top. And I take the integral of fx, subtract the integral of gx, because fx gives a larger area. So notice the difference. Earlier we have gx minus fx over x1 to x2 range. Now we have fx minus gx over 0 to x1 range. So I hope this gives an idea of what integration entails and the things to look out for when doing calculation of area under a curve.